Hello again. Coverage is at the heart of testing, and it's also at the center of the ARD optimizer. In this video, I want to explain how the optimizer generates paths and test cases from models based on the different coverage criteria. But in order to do that, you have to understand the fundamentals of coverage and the kind of more subtle meaning of different coverage criteria. So overall, I'm going to sort of talk about the meaning of coverage, just to get that clear, and just describe how coverage is used in two ways. Firstly, as a mechanism for measuring the so-called thoroughness or comprehensiveness of testing, but also when you have a coverage target, it drives the process of test design. You establish your target, you have things not yet covered, you create tests to cover a subset, and you reassess your position and you create more and more tests to cover more and more until eventually you achieve your coverage target. Now, this is what the optimizer does for us based on the models we create in the tool. So we have to understand how coverage works as a process before we can understand and take advantage of how ARD and the optimizer works. And I'll do a demonstration of the various levels of coverage on a typical model. And I'll make a summary at the end. To start this session off, I'm going to show a model in Agile Designer and use it to illustrate the way that the optimizer works when it's generating paths and test cases. So I'm actually going to use one of the examples that comes with the tool, the collegiate sports paging system. Now, there's nothing particular about this model that I'm going to worry about. It's a large model, as you can see, and I just want to use it to illustrate how the optimizer works. So if I go into Manage Path Explorer, we have the usual dialog. I'm going to choose, as normal, all possible paths and see what comes up. So if I generate all possible paths, you can see that I get 82 variations. Now, I'm not going to worry about the details of the model itself, except to say it's quite a complicated thing. The number of paths we get is 82, and we might think that's rather a lot of test cases for us to implement. So we have other choices that we can make when we generate the paths. So just beneath all possible paths, we have all pairs. And I'll explain what these things mean in the presentation itself. But I just want to illustrate how many tests we get if we use the different coverage or optimizations in the tool. So all pairs, what that does, it generates 51. So all pairs gives us a different subset and a different number of paths, as you can see. Let's keep going. All in-out edges. That creates 27 paths. Keep going. All edges. That's 27 too, which is interesting. All nodes should be the weakest of all the optimizations, and that generates 16. So all nodes would be simply covering all the elements of the model at least once in our paths. So that's how the path optimizer works. So have you seen, we've used the ARD optimizer to generate test cases from the model that we create. And the optimizer uses very clever algorithms to do this, of course, and it saves an awful lot of time compared with doing it by hand, obviously. Now, the concept of coverage underpins the whole process of how the optimizer works. So in order to take this further, we need to understand coverage in a much deeper way than perhaps you're used to. Coverage to most people means it's a measure of how deep or comprehensive or thorough your testing is. Now, the challenge we have is that very often when test cases are guessed or invented out of people's minds, there's no mechanism for measuring the thoroughness of what they're doing. In order for coverage to be measurable, it must be based on some kind of model, and that's the basis of ARD. Now, in general, the model could be any kind of pictorial representation of paths or behaviors of systems. So the model could be a state diagram, a flowchart, sequence diagram, or any other blobs and lines style representation. So any model that has nodes or blobs, processes, decisions, and then arrows joining these elements on your model, I would call them blobs and lines generically. Any model like this can be used to trace paths, and if you can count blobs and lines, if you can trace paths, you can define a measurable coverage target. And this is what ARD does for us. Now in an ARD model, clearly we can count nodes. These typically are processes and other elements, decisions and so on. And there are edges, the arrows that connect all the nodes together. And we can also count combinations of edges, and these would be subpaths within our model, and so on. Each one of these is called an optimization within ARD. And ARD generates paths that cover nodes, edges, or combinations in a minimum number of paths. The idea of the optimizer is that it generates test cases as a minimum number in order to achieve the level of coverage you select. This is what the optimizer does. Now, edges, nodes, and combinations of edges, for example, are what I would call coverage items. These are the things that you actually count. So when you set a target for a number of edges, nodes, or combinations. Now, if we were to do all this manually, with pencil and paper perhaps, we'd invent paths that exercise the coverage items and just keep track of them, make a note, and keep creating new paths until we have no coverage items left to cover. And that's how test design actually works. Now what the optimizer does is it performs this rather laborious task for us. This is what it does. So we choose an optimization, our coverage target if you like, and what the optimizer then does is it generates a minimum number of paths to achieve that coverage target. And each path through the model is in effect a test case, of course. Now the different optimizations generate different paths and different numbers of paths, as you've seen in the little demo I gave. Now all paths is the strongest optimization. It generates the most test cases, if you like. And all nodes is the weakest. All edges covers all decision outcomes. In effect, all the outcomes are the arrows in the model. Now you might know this as decision or branch coverage if you've taken an ISTQB certification class. The other optimizations need a little more explanation. Now all pairs is a useful technique in certain circumstances, and I'll demonstrate that a bit later. But all pairs basically represents every paired combination of outcomes from every decision. So for every arrow coming out of a decision, that is matched with every other arrow out of every other decision, and there should be paths to cover all those combinations as a pair. In-out edges matches every incoming arrow to a decision, and every outgoing arrow from a decision matches those as pairs, and then selects paths to cover each one of those combinations. Now I haven't talked about the probabilistic selection. In this case, the optimizer limits the number of paths and it weights certain outcomes above others depending on the defined priorities and probabilities. Now, again, this is a more selective and probably more restrictive coverage measure, but we can talk about that later. Now there's a relationship in general between the various optimizations in ARD, and I'll use this term subsumes to mean automatically covers. So for example, all paths subsumes, it automatically covers the all pairs optimization. All pairs subsumes all in or out combinations, and all in out combinations subsumes all edges, and all edges subsumes all nodes. So if you select, for example, all edges, the optimization, you automatically will cover all nodes in the model. So subsumes means stronger than, if you like. It generates more test cases. But stronger than does not mean necessarily that those test cases are a better selection. This notion of better or worse is not related to the count of test cases. It's more to do with the quality of test cases. Now, the optimizer isn't particular in terms of which paths it selects. It selects a minimum set. Now the probabilistic selection, what you get from that optimization varies depending on the parameters supplied. It's something that you can use to fine-tune your generated test paths. So let's take a closer look at the model that I looked at previously. So we'll go into Path Explorer again, and we'll choose all possible paths, and generate our 82 paths through the system. So there you go. Now it could be, if we were to be taking on the testing manually, the 82 test scripts to go through this feature would be far too expensive a task for us to do. So we might say that's over the top and we can't afford, if you like, to do all possible paths. It's not a sensible coverage approach. So we could say, well, instead of that, what we'll do is we'll cover all edges. And this would be much more likely to be the case if we were doing, for example, a system level test. All edges generates fewer test cases, 27. Now the other way to look at this is to say, although we can use the different optimizations to cut down or de-scope tests, if you like, we also need to pay attention to the level of coverage it generates. So if our concern was simply that we want to visit every feature, every process on our model, we might choose a very basic level of coverage, which is all nodes, and that would generate 16 tests. But then our users or our stakeholders might say, hold on, I'm much more concerned that we look at the decision making and we take the right decisions at the right time, at which point then you might look at all edges, and that might generate 27 tests. But then someone else might speak up and say, well, actually our real problem is our confidence in the decision making and the combinations and the routes into decisions. Are we getting these subpaths right? Are we arriving at the right decision and then making the correct decision afterwards? So it might be sensible in that case to look at either all in-out edges, or in an extreme case look at all pairs. So all in-out edges basically gives us confidence, or gives us coverage and therefore confidence, that we have all the combinations of ins and outs of every decision correct. So the optimizer allows us to think more deeply about the level of coverage we want to achieve, the cost of testing, particularly if we're doing it manually, and also the level of confidence that each of the techniques, each of the optimizations, if you like, give us. So let's summarize what we've learned so far. It's clear that the main drivers of your choice of optimization are cost and confidence. So the questions are, how many tests can I afford to build and run? If you have a very complex model with many thousands of test cases generated by the optimizer, it might be impractical. The other question, of course, is how much confidence does the optimization give me? Now, there might be some specific concerns you have whereby a particular optimization suits your purposes, and you have to look out for that. Now, all paths might generate thousands of test cases and be impractical, but all nodes is the other extreme, means that you have at least exercised every node on the model at least once. Now, the technique of all pairs covers every combination of input and has a particular value in configuration testing, which we'll look at a bit later. And all edges means every node and edge has been covered at least once, so it gives us a more general confidence. There is no best optimization because every optimization has a different cost associated. And so the value for money you get out of your optimizations is for you to decide. There are no fixed rules.